Recording, rolling. Yeah, it's Tuesday, February 4th. So starting on a new topic today. It's gonna be looking at fluids. Got some Paul Hewitt demos for you guys. Got some slides, some notes. Right on your thumbnail notes. This is gonna be a lot of these orange banners right now. Well, some of these are solids, but a lot of these are liquids. We're gonna be looking at in fluids. All right. Rotational dynamics quiz. Almost everybody turned this in over 2 weeks ago. Still have a number of students who haven't turned that in, but I want to get this back to you guys. You guys can do corrections the whole deal. And so tomorrow's the last day in taking that. So definitely double check focus, make sure you got it in. Most of you guys do already. Okay. Period 5, of course, is resiliency. So here's what I'm doing there. All right. Let's do fluids. Got some Paul Hewitt demos to kick this off.
Since the pressure is more against the bottom, what's to prevent that dam from scooting downstream? Especially when water seeps in here and you get these like little pebbles in here, like ball bearings. Why couldn't that whole dam start come downstream? It could do that, couldn't it? But you could stop it. You know what you can do? You can put a heavy weight on the top. Tons of lead. You could squash it right down, and that heavy weight would scrunch the dam right in there, and it would be held secure. But there's a better way. You don't need the big chunk of lead. You know what you do? You design your dam like this. Why? Now the water is going to push like this. Which brings us up to a little rule. A fluid will always push in all directions against an object, but all those directions will conspire to give a perpendicular force, right angles.
All right, you guys just catch what I said? Guys, if you have a tank of water, is the water pressure pushing against the side of the tank?
Yes, sir.
It always pushes in what direction? Huh?
All directions.
Which conspire to be?
All directions outward.
Here, I'll rewind a little bit in case you missed it.
It will always push in all directions against an object, but all those directions will conspire to give a perpendicular force, right angles. And so the weight of that water would hold that dam right against the bottom, just as a great big heavy lead weight on the top would. So pressure pushes in all directions, but the force of that pressure always turns out to be perpendicular to the surface upon which it acts. You know that's true because if you take a bucket and you put it in the water and you punch some holes in, no matter where you put the holes, when you put this down there, the water will spurt in. If the hole's here and you're dunking under the water, it'll spurt in that way. If the hole's on the bottom, it'll spurt straight up. Put an angle like that, it'll spurt like that. It will always spurt perpendicular to the surface.
All right, so that's pretty good enough. No, rewind here, rewind. Let's go way back to the beginning. Do you guys see these arrows right here? Guys, everybody look up here? Everybody look up here? So, talk about pressure. See, these sort of look like force arrows in a way. Guys, what's the connection between force and pressure? You guys remember this from last semester? Pressure is equal to force divided by what? Force per. You guys ever buy a pump from the store to pump up your tires? How do you quantify how much pressure is in your tires? PSI? Guys, PSI, that stands for pounds per square inch, pounds per square inch. And the answer is right there. Because pounds is like a force, and square inches represents a what? Square inches. Area. Guys, everybody focus here. So you guys know what area is. So if you ever to paint your wall, you know it's going to be an area. So, yeah, force per unit area. Now, of course, in this class, we're using metric units, so we're not using pounds and square inches. Guys, instead of pounds, how are we quantifying a force? Force is measured in newtons, right? Haven't we been weighing things in newtons since August? Okay. And area can be measured in not square inches, but square meters. Yeah, square centimeters, true. That works too, right? So how about, let's put it all together. Guys, could pressure be some force per unit area? This could be a Newton per square meter, right? In fact, that unit has a name. Starts with a P. 1 Newton per square meter. If you take a, here, help you guys visualize this. This right here, okay, I got 100 grams lab mass. This weighs almost exactly 1 Newton. It's like 0.98 newtons. I'll call it 1 Newton. Right? If I have that weight right there, because to pick it up takes 1 Newton, put it down, got 1 Newton of force. If I have a meter stick and I square this off, make a giant foam board that's 1 meter by 1 meter, so it's 1 meter squared. You guys get that? And I put this 1 Newton weight on that 1 square meter. That's an amount of pressure equal to 1 what? Pascal? You guys remember Pascal? It's a Newton per square meter. Right? You guys remember that? All right. So a little bit of review from last semester. You guys remember all that stuff? All right. So look at these arrows here. This could be force on, say, like some square meter here, and force per square meter here, force per square meter, right? Something like that. But you guys see how the pressure's going bigger, bigger, bigger the deeper you go? Right? And furthermore, let's see if this is about right. You guys see it's some depth, there's some pressure there. And at twice the depth, ooh, that looks like twice the pressure. And 3 times as deep is 3 times the pressure. 4 times as deep is 4 times the pressure. Is that also accurate, do you guys think? Like if you dive into a pool and you dive down, the pressure's definitely going up. Is the amount of pressure just very simply directly proportional to your depth? So if you dive 3 times as deep, it's 3 times the pressure? Ooh, I think it's also true too. Right? Now, I'm saying all these questions because I want you guys to sort of figure this out. Think, yeah, okay, I think that could make sense. These are all leading to formulas ultimately. You guys are going to see some formulas by the end of class today. Okay, so I'll lead to that. Where's my next? Let's get to the next video.
Since the pressure is more again. There's the rock under the water. There's some pressure against the bottom. That pressure pushes against the bottom with a force. There's pressure at the top. It pushes down with a force. Why am I making this arrow not so long as this arrow? This part's deeper. This part's deeper. That means there's more pressure. That means the water is forcing up against the bottom harder than at the top. Why am I making these arrows between the light size of that and that? Why? In fact, I can ask you a question, you can answer it. Why is it when you submerge something in the water, it doesn't start to just nudge sideways? You can see it. Check your neighbor. Okay, gang, let's look at it. We can see the rock is not buoyed sideways. Why? Because these forces are the same. And the force underneath is always going to be greater than the force on the top because it's deeper.
All right, so right now he's getting to, he's leading up to something called, guys, what force is it that keeps you afloat in a pool? That's called the what force? Buoyant force. Yeah, buoyancy, buoyant force. Okay. Why does the buoyant force specifically push you up instead? Like, why doesn't it push you down to the bottom of the pool? Right.
Is that thing got pressure?
Right, and it's right here, which is, yeah, if objects are 3-dimensional, right, you're some 3-dimensional object, right? The deeper you go, or the deeper part of that object feels more pressure, right? So the net effect is going to be to push you upward, right? Even if you're more dense than water and you do sink all the way to the bottom, suppose there was a scale at the bottom of the pool. You know, on land, you step on the scale and like, okay, I weigh like 500 newtons or whatever, right? But if that scale's at the bottom of the pool and you stand on the scale, does it read the same weight or less weight? Less, yes. It's not as much, right? Why? Because like there's still a buoyant force effect, right? This still lifts you up partially, even if it doesn't make you float completely. Okay. All right. Okay. So we got the direction of the buoyant force. It's going to be overall upward because the deeper part of the object, it's more pressure on it, more buoyant force. Okay. What about, can you quantify how much is the buoyant force? Like if you're stepping on the scale, say, hey, look, it looks like I lost some apparent weight. Like how much is that? Okay, so that's this next one right here. Right.
What I'm going to do, what I hope to do, is I'm going to dunk this in the water. And when I do that, this weight reading will go down, yeah?
All right, let's get some numbers here. Guys, real close to this one. There's a bunch of numbers flying all over the place, and we're going to piece together a formula, well, later in class today. Okay, so guys, this 1 kilogram mass, and this is 1 kilogram mass. I know it looks pretty big, but it's aluminum, which is not as dense as your guys, right? This 1 kilogram weighs how much according to the scale? At 10 newtons? Well, let's round it to about 10 newtons, real close to 10 newtons, right?
I mean, I can kind of show you over here. weight reading does go down. Would you say this?
Ooh, okay, now that needle's juggling around a little bit, but it's pretty close to what integer value right there? It's about six, right? And if I pause it right at the right point, it usually hovers right around the 6. Okay. So, ooh, the tension in the string is how much? 6 newtons? Because that's actually what the scale is reading, right? It's really just reading the tension in the string. Okay. But Earth is pulling on this object down with how much? 10 newtons. You saw it before, right? So, guys, what's the difference? 4 newtons? And that 4 newtons represents what? The force caused by the pressure, right? It's a buoyant force, right? Buoyant force, right? Because I know pressure would be a newton per square meter. Here we're just doing newtons. Okay. Let me draw this out for you guys. Draw this out. Or I think I got some notes from from earlier. All right, here we go. Okay. So let me cover up part of this. Do all this other stuff later. Okay. So here's his weight. His weight was weighed 10 newtons in the air, right? Then he dunks into water and the tension string goes down to 6 newtons. So now the scale only shows 6. And the other 4 newtons must be this buoyant force, the support force, right? Wonder how we can quantify that. What does that have to do with what variables, right? How about this? Because if he lowers it lower into the water or lifts it a little higher by a few centimeters, would these numbers change or no? Or would they stay about the same? What if this is like the ocean and he lowers it like a mile deep down into the ocean? Would this still be 6 and 4? Yeah. It turns out it would be. Right. So once it's completely submerged, now you guys know the deeper it goes, the more the pressure is building up, but there's no more pressure differential from the top to the bottom of the object. Right. So the amount of buoyant force overall would still be the same. It doesn't matter how deep it is. Right. How about this fluid itself, like the water? Ooh, guys, water has some density, right? What's the density of water? Who knows? 1 gram per cubic centimeter.
Yes.
Like if I had 1 centimeter cubed, or a little tiny box I could fit right here in my hand and fill up with yeah, that would be 1 gram. Okay? Guys, how about kilograms and cubic meters? Suppose I took a meter stick and I make a big old box, and it's 1 meter wide, 1 meter long, and 1 meter tall. So 1 by 1 by 1. And I fill that with water. How many kilograms is that? How about 1,000? Yeah, like 1,000 kilograms, right? Okay, so water has a density of 1,000 kilogram per cubic meter. Do you think that has anything to do with this 6 and 4 rating right here? Well, I know when it was holding this in the air, it was reading a different number, and air has a density too. Air is closer to 1 kilogram per cubic meter, right? So I think the density of the surrounding fluid would also play into this buoyant force formula, which we haven't gotten to yet, but yeah, just how do you guys think for now, right? Guys, everybody think about this? Okay. While I got this slide up, let's hit some other questions, right? Because earlier today, some of my other classes were wondering like, what would happen to if this was all sitting on a scale? So here I've got an empty container of water. Right? You guys see this container of water? And let's say it's sitting on a scale and it reads 20 newtons. I'm just making something up. Okay. That could weigh 20 newtons. Right. And now I'm going to dunk this weight into that volume of water. And the weight itself weighs 10 newtons and the string's hold up with 6 and the buoyant force is 4. That's all okay so far, right? Right. How much does this scale read now? Is it still 20 newtons or is it less than or more than 20 newtons? What do you think?
More.
More?
Yeah.
Yeah. Exactly how much should it read? It is more than 20. It's 20 what?
25.
Close.
24.
24 newtons. Okay. So one would think of it as sort of like this buoyant force that sort of alleviates tension off the string, right? Does get transferred down into the scale. Okay. Or you could also explain this with Newton's third law of motion. Yeah, the buoyant force pushes up on the object, and really just focus on the object with this free body diagram, right? But don't forget, the object also pushes down against the water with an equal and opposite force, and that gets transferred into the scale. So what was 20 newtons weight before, now it's more like 24 newtons, okay? So all right, so anyway, Got Paul Hewitt off midway through his demo here. Let's go back to here.
That loss of weight was equal to the support force? And that support force, we have a name for it, begins with BF. Buoyant force, okay? So the buoyant force can be seen by the loss of weight. Can't read that now, but read it now. Read it now, subtract the two, there's a buoyant force, yeah? All right, I'm gonna do it over here in this overflow can, but I'm gonna catch the water that's displaced, and I'm gonna weigh it. Whoops. This is not gonna be perfectly accurate, okay? But note now,
Okay, I meant to pause a little there. Because I want you guys to see exactly what the setup is. Okay. You guys see this little can right here? Okay. It's got some water in it too. He's about to dunk this weight into this can. Now, right now, the weight's 10 newtons. You guys see that? Okay. And do you guys see a little overflow straw right here? A little overflow, right? Yeah. So he's gonna, whatever water is displaced is gonna flow through this tube, and he's gonna catch it in the speaker. You guys see that? Right? Except some of it spilled out already. That's what he said. Oops, this is not going to be perfectly accurate. He lost about a ½ Newton of water. So this is going to be off by about a ½ Newton. But that aside, do you guys see this beaker weighs pretty close to 1 Newton? You guys see that? Right? All right, so you guys got these numbers, right? 10 Newton weight over here. 1 Newton this container weighs. Okay, let's check this out.
note now what the reading is of just holding, it looks like a little bit more than 1 Newton holding up the empty cup. Now, I dunk this in. This is losing weight, yeah? Because I'm displacing more and more water. There, now this has lost all the weight it can lose. This is still catching water. I want you to compare how much weight did this lose? The suspended weight. And how much weight did this gain?
Yeah, let's check that out. Ooh, this is down to about 6 now, isn't it? Just like it was before. So this scale lost how many newtons? Yeah, lost 4, right? 10 down to 6, lost 4. Okay. And this one, well, I'm going to round this up to about 5. Is that okay? Because he lost a little bit of liquid to start with. Okay. So it went from 1 to 5. Guys, going from 1 to 5, picked up how much? Also 4. Do you guys see it's a match? So what he's trying to show you guys is that the support force, the buoyant force holding this object up, is exactly equal to the weight of the fluid displaced. Do you guys see that? Okay. And later on today, you guys will see a more specific version of that formula, but he's setting up a formula here. Actually, what formula is he setting up? Does anybody know the name of this formula that he's setting up?
Oh, that's the Archimedes principle.
That is Archimedes' principle. That's right, Archimedes.
Do you see that they're the same? And that brings us to a very important rule with fluids. And that's this, that the buoyant force that acts on a submerged object is numerically equal to the weight of fluid displaced by the object. Okay? I didn't say the buoyant force is equal to the weight of the object over here. No, it's the buoyant force is equal to the weight of fluid, in this case, water displaced by the object. Okay, we see that? That's called Archimedes' principle. Air have any weight? It turns out air has weight, a lot of weight if you talk about a lot of air. Okay, what's it go here? 1 cubic meter of air. It's like this, huh? It's like about like this. Bam, bam, bam. 1 cubic meter of air, like a little small truckload, right? Has 1 1/4 kilograms. Okay, that's about 2 3/4 pounds. So try this tonight when you go home. Open up the fridge. Now your fridge is about 3/4 of a cubic meter. Ask the people at the house, hey, the air inside there have any weight? What are they going to say? Yeah, it's got some weight. See that big grapefruit sitting there on the shelf? Does that have any weight? Yeah. Say, which weighs more, the grapefruit or the air? Take a guess. You get about 2 pounds of air in there. And if that grapefruit's less than a 2-pounder, then the weight of air in that refrigerator is greater than the weight of, so greater than the weight of a dozen of eggs. Dozen of eggs weigh less than the air in an ordinary size refrigerator. Hi gang, atmospheric pressure time. Colored water, card, turn it upside down, and it stays. Now, wouldn't you think the water pressure would push the card away? But there's another pressure around stronger than that water pressure, and that's the air pressure, the pressure due to the atmosphere. The atmosphere at 20 miles high is squashing in this glass a lot more than the water's pushing down.
If you guys remember how much, right? You guys, did you guys see maybe like a few centimeters water there? I don't know, 10, 15 centimeters, something like that. Okay. How tall would this column of water have to be to match the air pressure pushing up from, pushing up on the card? How tall would that have to be? You guys remember this from last semester? Here, let's say the same question in a little bit different way. Is like right now we're all sitting in atmospheric pressure, right? Which is some amount of pressure compared to the vacuum of space would be 0, right? And we're definitely at 1 atmosphere, right? What if you jumped into a pool and you started diving down? And the deeper you go, you can feel that pressure going up, 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 right? At some point, you'll hit an additional atmosphere to get you up to 2 atmospheres, right? So now we're sitting in 1. At the bottom of a pool, maybe you're up to 2 atmospheres. How deep would you have to dive to get to an additional atmosphere? Because it's the same answer. You guys remember 10.3 meters? You guys remember that? 10.3 meters, right? About 30 something feet, like that. Okay. All right, so how about some other ways to quantify pressure? So we're sitting in 1 atmosphere pressure. Do you guys remember how many pascals that is? Yeah, 100,000. That's right, 100,000 pascals. I think the definition is like 101,325, something like that. Okay, let me quantify that for you guys. So here's 100 grams, which weighs about 1 Newton. So if I lift it, it takes 1 Newton to lift it, right? But if I made a big old foam board that was 1 meter by 1 meter, and I put this 1 Newton of weight on it, wouldn't that represent 1 Pascal of pressure? Because that'd be 1 Newton per 1 square meter.
Pedro Pascal.
Huh?
Pedro Pascal.
Yeah, I think name after that. Or wait, no, is it?
Yeah, it's a guy.
No, never mind. Different Pascal.
No, yeah. Oh yeah, but he
Was it Blaise Pascal? I think.
He's playing it. He's in the Fantastic Four though.
Yeah,
It
but
was Joel. Come on.
Yo.
Wrong. Yeah.
Different Pascal. All right. Okay, so back to here then.
That pushes the card up a lot harder than it's being pushed down. And I can show you atmospheric pressure in action with these cans. I have some heated water, and the water molecules going very fast inside there. What would happen if I slow those water molecules down?
Right. So, but what you guys predict before you see it, right? So, if you want to do this at home, what you're always doing, how make this work really well is to put a little bit of water in the can. You know, he's heating them up. You guys see like a hot plate over here? Right, he's heating them up. Okay, so I bet a lot of this water is like evaporating away. Got a lot of water vapor, very hot water vapor. He's going to dunk it upside down into this cold water right here. Now, when he dunks it upside down, isn't that effectively going to seal the top? Right? Because these are empty cans, other than there might be a little bit of water in them, but they're empty cans. They're open to the atmosphere. But if he dunks upside down, it's effectively going to close it, isn't it? Right? So whatever vapors inside is going to be trapped in there. Okay? And the temperature is going to plummet because right now it's really hot. That's why he's not touching it with his hands. He's got those tongs, right? But he dunks it in that cold water, the temperature is going to go down. Okay. Oh, and this is all in 1 atmosphere of pressure. So is that going to create a pressure differential? And what's going to happen to the can? Let's see.
What happened to the pressure inside the can? Let's try it and see. I'll dip it in this cold water. And another. What happened here? Reduced pressure inside, but the pressure outside, just the same. And cruncheroonie, pressure difference can be very, very dramatic.
All right, so later today, when you see something called ideal gas law, think back to this one. I'm going to show you guys ideal gas law.
Physics is fun. And we talked about wood floating, and you guys know why wood floats, because the buoyant force acting up equals the weight acting down. Isn't that true? In fact, isn't it true that anything submerged in a fluid will be buoyed up by a force equal to the weight of the fluid? Now, we said fluid and not liquid. Why? How about someone says, I can see why a fish doesn't sink, and I can see why a hunk of wood doesn't sink, but I don't see why that air-filled balloon doesn't sink. Wait a minute. If you see one, you got to see the other, because the air-filled balloon is displacing area. And isn't there a buoyant force on the air-filled balloon? And if that buoyant force is more than the weight of the balloon, what will the balloon do? It'll go up. If that buoyant force is equal to the weight of the balloon, what will that balloon do? Stay there. And if that buoyant force is less than the weight of the balloon, it will sink. So if I take a balloon, I blow it up with air, and I let it go, it sinks. Why does it sink? The balloons you see at the end of the string at the circus, honey, those are filled with helium. Okay? But why is it you blow your own up with air and it sinks? How about that air, gang? Is that air more dense or less dense than the air outside? It's a little bit more dense. Do you know why? Because the stretched rubber is tending to compress it. So it's slightly compressed. So it's more dense than outside. That means its volume of air will weigh more than the equal volume out. It's just going to sink. But you use helium. The helium is very, very light, not as heavy, huh? Each molecule is not as heavy, so it is not as dense. So the helium-filled balloon is simply lighter than the buoyant force, and up it goes.
Ooh. All right, Bernoulli principle. All right, so you guys see that ping pong ball, pendulum right there. He's going to turn on the faucet, and when he does, a stream of water is going to hit that ping pong ball. And what do you think is going to happen then? Check this out. You guys saw that ping pong ball got vacuumed in place? Rewind a little bit, just in case you missed it. All right, so I think there's something going on with. Do you guys think there's like a thin film of water that's going around that ball? Right, so can it go pass through on the other side? Okay, so got this fast-moving dense fluid, right? Because the air is about a kilogram per cubic meter. The water's like 1,000 times that. Water's about 1,000 times as dense as air. Okay, it's going around the ping pong ball really fast. And guess what would vacuum a ping pong ball in place? Would that be a high or a low pressure? That'd be a low pressure to vacuum it in place, right? So something to do with like a fast-moving fluid is going to result in a low pressure. Right? I can show you guys that also with, come on here. Right, it's called Venturi effect. Venturi effect you guys are seeing right there. Close this one. Okay. So this is really just an application example of Bernoulli principle. Okay. We've got some slides for this. You guys are going to see in a few minutes. But let's kind of make sense of this. Now, there's two different fluids here. You guys see a fluid in the bottom and a different fluid in the top? Because I see some lines here, right? Actually, these lines aren't matched. There has to be some kind of pressure differential that's pushing down the right side and vacuuming up the left side. Is that right? Now, I don't know what these fluids are, so I'm going to call the bottom fluid water and the top fluid oil. I don't know. It's exactly true, but it could be, right? Maybe it's water down here and oil up here. Is that okay? Right. So see if you guys figure this out. Guys, where is there more pressure? Is there more pressure on the right side or more pressure on the left side? Who says there's more pressure on the right side? Who says more pressure on the right side? Yeah, that would have to be the case, right? It's like pushing down. See, it's pushing down. The left side's getting vacuumed up, right? All right. So why is that? Well, part of what's going to lead us to something called conservation of flow. Okay. So let's look at the fluid in the top, like this oil, I'll call it. Right. Now they've got it flowing right to left. Although if it was going left to right, you actually wouldn't be able to tell the difference because the pressure differential would look exactly the same. Right. So I don't really know the direction of flow. It doesn't really matter. But it does matter that it is flowing. Right. In fact, if you know the density of these materials, like if you know the density of this oil and the density of this water, there's enough information just from that picture. Like if you know this height change is like so many centimeters, you could calculate how fast the oil on the top is flowing, right? As long as you know the densities, right? Right. Let's think about flow speed, or no, let me back up. How about flow rate, like volume per time? Okay. One way to quantify volume per time could be gallons per minute. Right? You guys probably heard, right? So is it an equal number of gallons per minute flowing in this big pipe as in this little pipe over here? Same gallons per minute? You guys think? Yeah, it's the same gallons per minute, or in this class we'll call it cubic meters per second, but it's the same flow rate. We'll call it conservation of flow, right? Now, what about flow speed? Like, which has a greater linear speed? And now this is going to be different, right? The water in the, or sorry, I meant oil, right? Let's call it oil. The oil in the big pipe or the oil in the little skinny pipe? Which one's moving faster in terms of linear speed? Yeah, the little tiny pipe. You guys think? Right. And if you weren't sure, then here's some ways to think about it. You can always take things to extremes, and sometimes that'll illuminate a situation. So what if the little pipe was like a little tiny straw, and the big pipe was like the size of an ocean? Okay. Do you guys see now? It definitely make more sense that maybe the ocean is not really moving, but once it gets to the straw, it takes off real fast, right? Or you could reverse it. You could have it going left to right, okay, and have the same effect. So what if you have a straw leading into the ocean, and you have just a bunch of water going through the straw really fast, but when it hits the ocean, it's going to slow way down, right? Okay. So I'm trying to hint at there's a more proper formula I'm going to take you guys through later today, but it's called conservation flow. So the flow rate's the same. The individual linear speeds are different, and connect that with that ping pong ball you guys just saw. A fast moving fluid, which would be in this little tiny straw on the left side, is going to result in a pressure decrease, and that's what vacuumed the ping pong ball in place. Okay, which is also why this left side is lifted over this right side, right? Because there's less pressure on the left side. You guess that too? Okay, so moving fluid will result in a decreased pressure. Okay, all right, let's see what slides I got here today. The slides. All right, whoops. Okay, start with this one right here. States of matter. All right, so our main focus is going to be like fluids and liquids, but here, let's look at all of them. Okay. So your main three states of matter, you got solid, liquid, and gas. Now there's definitions for each of these. So I'll give you guys some real shortcut type definitions. Okay, so solid is something that wants to maintain its shape and also maintain its volume. Right. Now, of course, there's exceptions to all these and weird rules like what is Play-Doh? It's like, it's kind of hard, right? A liquid is something that wants to maintain its volume, but not its shape. So it'll fill whatever container it's in. Okay. Again, there's exceptions to that. You can have compressible fluids, but in this class, we're mostly working with liquid water, which is basically not compressible. So it doesn't matter how much pressure you put on the water, it'll pretty much stay the same volume. So it's not really compressible, right? And a gas is something that is easily compressible, so it can change volume and also change shape, right? So both those things, right? So there's your main three states. Okay? You guys see going left to right, like how do you go from here, let's consider water. If you have an ice cube and then it melts into a liquid and then that vaporizes into a gas, could you be increasing the temperature? Right? Going increasing temperature left to right, right? That's not the only way to have a phase change. You could also play around with the pressures, but just to simplify this a little bit, right? But if you keep heating up a gas, eventually you get this state of matter, plasma. When I flip the fluorescent lights on, that's an example of a plasma. There's some electricity going through the bulb, right? Where the electrons are stripped away from the nuclei. Right? If you keep heating up a plasma, you can eventually like tear apart the nucleus and create this quark gluon plasma, which that's a really extreme situation there. Maybe like the early universe, maybe even some of that. Right? Okay, let's go the other way. So what if you cool that off, cool, right? Now we got a frozen solid, right? What if you keep cooling a solid? You get near absolute zero temperature, right? Like here, guys, the temperature in this room, if you want it to be colder, maybe I could kick on the air conditioning and make it colder, right? Make it colder, right? What if you keep getting colder, and now you're like Antarctica level cold, so it's like crazy cold, and you keep going colder. Do you think that there's some bottom temperature where you can't get any colder? You guys think? Right? And guys, what's that lowest temperature in the universe called? It's called
0 Kelvin.
Yeah, 0 Kelvin. Yeah, absolute zero. 0 Kelvin, absolute zero. Yeah, right. So like a fraction of a degree above that, you can reach this really weird state called Bose-Einstein condensate. Anyway, so there's a big picture of some states of matter right there. Okay. All right. Sorry about these temperature scales a bit. So historically, the first scale that came around was Fahrenheit, right, followed by Celsius, followed by Kelvin. But what's the difference in these scales and what are they all useful for? So since we live in the States, maybe Fahrenheit is useful for like a weather report, something like that, right? And there's a history of where these numbers come from. Like, you guys know water freezes at what temperature in Fahrenheit? Yeah, 32 degrees. Right. Again, there's a weird history behind that. But let's just run with that. And it boils at 212. Right. Seems kind of arbitrary, but there you go. Right. When Celsius comes around, they say, well, let's standardize that a little bit. A lot of the properties of the metric system are based on water. Like density of water is exactly 1,000 kilograms per cubic meter. Right. So you can play off that. It's kind of where a kilogram originally comes from. Right. So hey, let's have water freeze at 0 and boil at 100. Right. That's easy, right? But even that's only true at 1 atmosphere of pressure, that water boils at 100 degrees Celsius. Right? So It's not really universal. It's just maybe a little bit more handy, right? So scale a little bit different. Okay. Now, if you want to get to absolute zero, these three scales side by side, try to make them align. So the numbers pretty much align, maybe off by a little bit decimal place. Okay? In terms of Fahrenheit, the lowest you can go is negative 460. There's no such thing in the universe as negative 461. Okay? You hit negative 460 and then you're just kind of out of energy at that point. Okay? At Celsius goes to negative 273. Okay? What's special about the Kelvin scale, guys, if Celsius and Fahrenheit are relative scales, because you can go negative, but it's not like there's a negative amount of anything. It's just a relative scale. Okay? Kelvin is not a relative scale. Kelvin is a what kind of scale? Starts with A.
Alphabet.
Absolute scale. Yeah. Right. So if you double the number on the Kelvin scale, you're actually doubling the temperature. Right? You guys see that? Right. That's now really the only reason I'm showing you this slide is because you have to apply that to be able to work ideal gas law. Right. And so let's talk about gases a little bit. I think this might be the only slide I have that really pertains to gases, but hey, show of hands. How many guys learned about ideal gas law in a past class? Maybe chemistry, possibly? Yeah.
Learned about in the past life.
Yeah. Oh, past life. Or that works. So remember it. Right? So, P got the pressure inside this gas. V is volume. So how big is that balloon? Right? T is temperature. Benosis says absolute temperature, right? Because it shows how these variables are proportional to each other. Now, really, this pressure, volume, temperature, those are come from. There are some laws that lead into this. I think it's called Boyle's law. I think it is P and the V. Let's see, I think it's Charles' law relates to this V and T, says those are directly proportional. And then I think it's Gay-Lussac says pressure and temperature are also directly proportional, right? But if you put them all together, right, get a big picture, right? There's all together. PV equals nRT, right? Right. So got P pressure, V volume, T temperature, absolute temperature. How about these other ones? N is a count of how many gas molecules for this ideal gas. So if I have a balloon and the balloon's tied off, so it's all sealed off from the outside world, okay? There's some amount of gas molecules stuck in there. Or earlier today, you saw Paul Hewitt dunk a soda can upside down. Okay? So there's like some number of molecules inside that can. Right? So that's N. Right? And this R is just a constant to tie everything together. Because there's different ways to quantify any of these. Like pressure, you could quantify pressure in how many atmospheres, or you could do how many pascals, or PSI for that matter. Right? Volume, you can quantify volume in cubic meters. You can quantify volume in liters. You could quantify, right? There are different ways to quantify anything. So there are different values of R just to make the numbers match. Something, right? Okay, you guys get that? Okay. But maybe the biggest thing I want you guys to get out of this is, do you understand the proportional relationships? Right? So how about this? Let's start with pressure and volume, right? That relationship, like Boyle's law, right? Let's say that balloon right there. You guys see that balloon? Let's say you squeeze on the sides of the balloon and you're like squeezing it down smaller, smaller, smaller. You guys got that? Let's say the temperature is staying about the same, so the temperature's not really changing, right? But the number of gas molecules inside, okay, that's also constant. So I'm squeezing down the balloon. Guys, if I'm squeezing down the balloon, what's happening to the volume? The volume's getting smaller, right? Right, because I'm squeezing it down, the volume's getting smaller. At the same time, what's happening to the pressure inside the balloon? It's increasing, isn't it? If you're a fly flying around inside the balloon, you feel the pressure go up, right? Is it too? Right? So inverse relationship between the two. Guys, what if you have half the volume? If you have half the volume, you have how many times the pressure? Yeah, 2 times, double. Right? So double and half, right? Like that, at the same temperature. Right? Let's bring in, how about temperature, right? So let's keep the balloon. Let's say pressure is about constant, just to keep a variable constant, right? What if you heat up the balloon? Guys, if you heat up the balloon, what happens to the volume?
It expands.
Yeah, it's going to expand, increase, right? What if you double the temperature? Guys, if you double the temperature, the volume is going to
Double.
also double. You see double? Because that's a direct relationship right there, isn't it? Okay. Now the catch is, here, see if you guys figure this out. What if you go from 10 degrees Celsius? You guys ready for a real tricky question? Guys, everybody look up here? Real tricky question. What if you go from 10 degrees Celsius to 20 degrees Celsius? You guys got that? Right? The volume will go up by about how much? How many guys say double?
I say triple. Half? No, it's half.
What?
It's half.
You're going from 10 degrees to 20 degrees. You're warming up, right?
JK, let me know.
So shouldn't the volume go up?
Mhm.
How many guys say it'll go up, but less than double? Yeah. How many guys say it goes up? Here, let's figure this out. Guys, I just told you the temperature. What temperature did I just tell you?
10 sort of.
Celsius.
Oh.
Celsius. Guys, if I flip back a slide right here, if I go from 10 degrees is right about here to 20 degrees is right about here, in terms of a proportional change, I'm moving it with my mouse cursor. You can barely tell. Isn't that just a tiny, tiny change? Hey, guys, if you ever apply this ideal gas law and you put numbers in here for temperature, you cannot use Celsius. You have to use what?
Kelvin.
Kelvin. Right. So let's see how much the volume of the balloon actually went up. So first I have to convert to Kelvin. All right. Okay, I have to go way back. I should have. It's this one right here. Okay. You guys see K equals C plus 273. Right. So if you want the temperature in Kelvin, take your Celsius values, like I said, 10 and 20, and add 273. Right. So let's do that. So go back to here. Right. So 10 plus 273 is like 283. And 20 plus 273 is like 293. Right. So what is 293 compared to 283? So I just divided that in my calculator. And I got 1.035. You guys got that? Okay. 1.035. So go back to this balloon. If you go from 10 to 20 degrees Celsius, which in terms of a Kelvin scale is a factor of 1.035, the volume of the balloon should increase by how much? Yeah, 1.035, right? Which is about 3.5%. Okay, about 3.5%. So it goes up, but not very much, right? Right, you guys got it? Right, there you go. Ideal gas law. All right, let's look at yeah. All right. Here's what I'm gonna do. Yeah, today's been kind of weird pace. So I have a few more slides that relate to those demos that you guys saw Paul Hewitt do. I'm gonna flash these a little bit fast, and then maybe tomorrow we'll go over these a little bit slower. Right? So, guys, what is this Greek letter right here called?
Values.
It's called rho. It's called rho. Okay. And in this class, it usually stands for density. Okay. There's some other applications too, but in this case, it's density. Guys, density is a ratio of what to what? Yeah, mass over volume, mass compared to volume. And that's some intrinsic property of some material. So aluminum has some density, lead has some density, right? Water has some density, right? Something like that. Right. Ooh, hey, is this the experiment that Paul Hewitt just did with Archimedes' principle? Now, my number's a little bit different, so maybe we got a slightly different density object, right? But what Paul Hewitt was showing you was that the buoyant force, the support force from the water that's trying to make you float, is exactly equal to the weight of the fluid displaced. Here's where we had this overflow can and something like that, right? So if this object weighs 10 newtons, and you dunk into the air and the tension goes down to 7 newtons, the other 3 newtons must represent the weight of the water that's displaced. Get that? Okay. Now we can go an extra step with this. So weight of fluid displaced. Guys, weight, isn't that equal to mass times gravity field? Mg? That's what we've been calling it all year, right? Weight is mg. Okay, so I got a g right here. I'll put that right here for gravity field. So if you were on Mars, would the numbers be a little bit different on Mars? Yeah, because the gravity field's different, so it would work out a little bit different on Mars. Ooh, right. Oh, right. Now how about mass? Well, mass can be density times volume, right? And we're talking about the mass of water displaced. So we're talking about the density of water here, not the density of the object, but the density of water. And this V displaced is, well, just how much water was displaced. Now, if the object's completely submerged, it would also be that volume, right? But if the object's like floating on top of the water, then it's just however much water is pushed out of the way, which is less than the volume of the object. Okay, so look at that. Right. Here, let's get pressure on the right side. The deeper you go, the more pressure. You guys remember that from earlier today, at the beginning of class? The deeper you go, the more the pressure. Right? We were saying, okay, well, it's probably proportional to depth. Right? And that's exactly what this formula right here says. Okay? So pressure is proportional to depth. If you're 3 times as deep, you get 3 times the pressure. Okay, see that? It also matters what the density of the fluid is. Right? And also the gravity field of the planet. Hey, that matters too. So again, if this was on Mars, you get a different pressure on Mars. Yeah, because there's a different gravity field on Mars. Right? Right. Now, this pressure differential is going to somehow result in a buoyant force that goes back to this Archimedes principle here. Right? Here's Archimedes principle all over again. Okay? So this is a good setup for this iceberg question. Okay, see these two? Both have a floating iceberg. Right? So one of the classic questions I like to ask every year is like how much of an iceberg is submerged, and that really depends on what's the density of ice compared to the density of water. Right? And the answer is well right there, but probably go over that more slowly a different day. Right? Pascal's principle. Do you guys see a hydraulic lift right here? I have in front of me. I have a pulley system. You guys remember pulleys last semester? Pulleys in mechanical advantage. You guys remember that? Right. You can also have a hydraulic lift. You can lift something really heavy with a small input force. And the principle here, Pascal's principle, is that the pressure is the same all the way across this hydraulic fluid. So the pressure is transmitted undiminished, right? So the pressure on the left side, pressure on the right side is the same, right? Pressure is force per unit area. So you can have different forces on different areas to match the pressure. You can lift something heavy with a small input force, right? A little bit more of that. Right. Conservation of flow. We're gonna have to save this one for tomorrow. Bernoulli principle, it leads into Venturi effect. Okay. All right, so all those are coming up, but we're gonna save some of those for tomorrow.